Hello everyone. This is lecture number 6 of engineering mechanics. The contents of this session are types of forces, equilibrium, conditions of equilibrium, and then we are going to study about free body diagram and then Lam's theorem. So we are going to solve the problems based on Lam's theorem and then equilibrium of coplanar concurrent force system which involves single bodies. These are the contents of this session. Let us start with types of forces. You can see in the screen there are different types of forces. Let me repeat it. First, you can see there is a frictional force, and then you can see the gravitational force. You can see the apple is falling towards the earth or towards the ground due to gravitational force. And the next one is magnetic force. Okay, so and the fourth one in the first row is the applied force. You can see there is a person applying the force on a block of mass m, and then that block is moving with the velocity of v. Okay, next one is beyond force. Okay, and the next one is tension force. You can see there is a block which is tied to a rope, and then that rope is tied to the roof there with the help of hooks. We have to see what is the force acting on the rope, and then what is the force exerted on the block, and then what is the force exerted on the wall over there. Or okay, and the next one is drag force. You can see the drag force on the vehicle displayed over there, and the last one is spring force. Okay, this kind of example you might have seen in the motor vehicle, that is two-wheel vehicle over there. Okay, these are some of the examples of types of forces there. Types of forces acting on a body. Let us discuss some of the forces which are acting on the body. First one is applied force. What do you mean by applied forces? Applied forces are the forces applied externally to a body. Okay, that is which are applied from the external source, externally to a body. Next one is each of the force has got a point of contact with the body there. Fine. Next one is if a person stands on a ladder, his weight is an applied force. Okay, you can see here the weight of the person is coming on the ladder, that is called as applied force. Let me repeat it once again about the applied force. Applied forces are the forces applied externally to a body, and then each force has got a point of contact with the body. If a person stands on a ladder, his weight is an applied force. Here you can see this is the weight of the person, and this is acting like a applied force on. The next one is non-applied forces. There are two types of non-applied forces. First one is self-weight and the next one is reaction. What do you mean by self-weight? Self-weight is like every body is subjected to gravitational acceleration and hence has a self-weight. If the body doesn't have a self-weight, then it is not subjected to gravitational acceleration. If body is having self-weight, then it is subjected to gravitational acceleration. So this self-weight is calculated using the formula W equal to mg. W equal to self-weight of the body, is m equal to mass of the body, and then g is the gravitational acceleration. Okay, self weight always acts in vertical downward direction. Okay, I'll repeat it once again. Self weight always acts vertically downward direction. Next one is when analyzing equilibrium of a body, self weight is treated as acting through the center of the gravity of the body. Okay, so whenever you want to analyze any body, okay, any body. Okay, so this is my body here. Okay, so we have to assume that self weight is acting exactly at the center of the body or center of gravity of the body here. Okay, and the next non-applied force is reaction. What do you mean by reaction? These are self-adjusting forces developed by the other bodies which come in contact with the body under consideration. I'll repeat it once again. These are self-adjusting forces developed by the other body which come in contact with the body under consideration. Let me explain here. So this is my ground surface. Whenever you apply a force on the ground surface with some intensity, the ground is going to exert equal and opposite force. That is called as reaction force. The example of applied force and then non-applied force. You can see on the screen, there are two figures displayed on the screen. Okay, and the left one is the example for the applied force and the right one is the example for the applied force. So non-applied force. Okay, so let us discuss the first one, that is applied force. Applied force, you can see there is a hammer and then you are hitting a nail over there. Okay, when you apply a force on a nail, it is going to move downwards. Okay, this is the example of applied force. Coming to the right hand side, that is non-applied force, we have a table over there. On top of table, a material is placed. That is called as non-applied force. Okay, so you are not applying the force but you are just placing it. Okay, that will not act like a applied force, it will act like a non-applied force. Okay, and then you can see there the weight of that particular material is coming downwards and then the reaction from the table is coming upwards. Okay, that is represented as n, and then the self weight of the body or the material which is coming downwards is represented as w. The free body diagram of this is represented towards the right, bottom right of the screen over there. Fine, these are some more examples of applied force and the non-applied force. To the left hand side you can see there a ball is been hit by the player over there. Okay, that is the example for applied force. And then next one is the ball is at rest on the ground. Okay, so that is the example for non-applied force. You can see there the reaction force, the friction force, and then the weight of the body over there or else the ball over there. Fine. Next one is equilibrium. What do you mean by equilibrium? The term equilibrium implies that either the body is at rest or the body is in static equilibrium. When the force system acting on it tends to produce no net translation or rotation of the body. Okay, I'll repeat it once again. The term equilibrium implies that either the body is at rest or the body is in static equilibrium when the force system acting on it tends to produce no net translation or rotation of the body over there. You can see there in the first figure over there, there is a person standing over there. The weight of the person is coming downwards and then the reaction is coming upwards over there. This is the person who is standing still, or we can also call it as stationary person. He is not moving, he is in equilibrium over there. The free body diagram of this person is drawn here. Okay, so similarly you can see here the weight of the person is coming downwards and then the reaction is moving upwards. Okay, so this is the example of equilibrium there. Okay, so you have to be very careful in understanding this statement over there. Okay, what do you mean by equilibrium? This is very helpful when we solve the problems in the coming session over there. Conditions of equilibrium. There are certain conditions of equilibrium. Let us study one by one about the conditions of equilibrium. So the first condition is algebraic sum of all the vertical forces must be equal to 0. Okay, suppose if there are vertical forces which are acting on a body, the algebraic sum of all the vertical forces must be equal to 0. Then only we can call it as the body is in equilibrium. This is my first condition. Let us go to the second condition, that is algebraic sum of all the horizontal forces must be equal to 0 there. Okay, so whenever a body is subjected to any horizontal forces, the net effect of all these horizontal forces must be equal to 0. Then only we call it as the body is in equilibrium. And the last one is algebraic sum of moment of all the forces about any point must be equal to 0. Okay, so these are the three conditions of equilibrium. I'll repeat it once again. That is, first one is algebraic sum of vertical forces must be equal to 0. That is the first condition. And the second condition is algebraic sum of all the horizontal forces must be equal to 0. This is the second condition. And the third condition is algebraic sum of moments of all the forces about any point must be equal to 0. These are the three conditions of equilibrium. These conditions are very useful and very helpful whenever we solve the problems in mechanics. These are very important conditions of equilibrium. The next topic is equilibrium. What do you mean by equilibrium? What is the definition of equilibrium? The definition for equilibrium is force which is equal and opposite to the resultant force is called as equilibrium. Okay, I'll repeat it once again. Force which is equal and opposite to the resultant force is called as equilibrium. You can see from the figure over there what is the direction of equilibrium and then what is the direction of resultant over there. Okay, so there are two forces F1 and F2 which are acting at a point here. Okay, there are two forces F1 and F2 which are acting at a point here. The resultant of these two forces is represented in this direction. This is represented as R. So what is equilibrium? It is the force which is equal to and opposite to the resultant force. Okay, if the value of, for example, if the value of resultant is 10 kilonewton, the which is acting in this direction, okay, so value of equilibrium will be 10 kilonewton only, but it will be acting in opposite direction. Okay, so this is the first example. Coming to the second example, here you can see F2 is acting here, F1 is acting here, and then R is acting in this direction. That is the resultant of these two forces F1 and F2. So what is equilibrium? Equilibrium is equal and opposite to the resultant force. You can see the resultant is acting in this direction, equilibrium will be acting in the opposite direction. These are the two examples of equilibrium. The next topic is free body diagram. As I was telling in the previous slides over there, I was just discussing or telling free body diagram of this person, free body diagram of that block. So what do you mean by free body diagram? It is a sketch or a diagram in which a body is shown with all the external forces acting on by making it free or detached or isolated from its surrounding body. Okay, so you can see the example here. It is the sketch, this is the actual diagram here, and then this is the free body diagram of the same actual diagram here. Okay, so this is the actual diagram. You can see the person is holding a bar over there, and then it is tied with the rope over there. Okay, and then this is the mass m, and then the self weight of the body or the mass is acting downward over there. Fine. So now you can see there it is a sketch or a diagram. This is the sketch or a diagram in which a body is shown with all the external forces. You can see these T and W are the external forces which are acting on a body, and then these are detached or isolated from its surrounding body. This is my surrounding body of this mass. This has been detached, and then only the forces are represented. This mass is taken as a circle over there. That is the external bodies, that is the surrounding body is isolated or detached. So this is how the mass is represented here, and then there is a tension force which is acting upwards, and then the self weight of the body which is acting downwards. This is called as free body diagram of this actual diagram. I'll repeat the sentence once again. It is a sketch or a diagram in which a body is shown with all the external forces acting on by making it free or detached or isolated from its surrounding bodies. This is called as free body diagram. In mechanics, in engineering mechanics, whenever we want to solve any problem, the very first step is we have to draw the free body diagram. Without drawing the free body diagram, you cannot solve the problem. It's very difficult to solve the problem. So always when you solve the problem, the very first step is free body diagram. That means you should always represent what are the forces which are acting on the body in free body diagram. And then once you draw the free body diagram, you can easily write the equations or solve the problem. So this is very important in engineering mechanics course, free body diagram. Okay, this is the example for free body diagram. You can see there are two poles which are present over. This is pole 1 and this is pole 2, and then to these two poles there is a rope tied together. Okay, so there is a rope which is tied between pole 1 and pole 2. On top of this rope a person is standing exactly at the center of the rope. Now we have to draw the free body diagram of this actual diagram over there. Okay, well, actual diagram in this is there are two poles, and then there is a rope between these two poles, and then a person is standing on the rope over there. Okay, let us find out or write the free body diagram of this figure over there. Okay, so you can see there this is the free body diagram of the given form diagram over there. So first I'll represent the weight of the person which is acting downwards. When this person is acting or standing on this rope which is moving downwards, there will be tension in the left side of the rope and then towards the right side of the rope. Why? Because this rope is tied towards the left side and then tied towards the right side also. That's why there will be tension along the left side of the person and then towards the right side of the person over there. So that's why we have taken it as TL, tension along the left side and tension along the right side. So this is my free body diagram of the given figure here. Okay, so I'll repeat it once again. This is the weight of the person who is standing on the rope which is acting downwards, and then due to his weight there will be tension along the rope towards the left side and towards the right side. So this is how the tension towards the left side is represented, and then this is how tension towards the right side is represented. And then you have to always identify the axis of reference there. Without identify the axis of reference, it's very difficult to solve the problem, and then you cannot solve the problem only at some situations. So always we have to identify the axis of reference, which is my axis of reference whenever we draw the free body diagram over there. Now here we can say that this is my x-axis and then this is my y-axis. Okay, so it is having certain inclination over there. This free body diagram is having certain inclination. That is, let me draw a horizontal line here. Okay, so the angle made by TL is 5 degrees with respect to the horizontal, and the angle made by TR with respect to the horizontal is again 5 degrees. Without writing the angle made by these forces in the free body, without writing these angles in this free body diagram, is it is not complete over there. So always you should include all the angles made by the forces, and then what are the forces which are acting on the body, and then the direction of forces should also be mentioned in free body diagram. So this is the example. So let us study some of the different types of figures for free body diagram. Here you can see there is a rope tied to the wall over there. Okay, so and then there is one person holding the rope towards the right hand side of this platform over there. Okay, and then one more person is hanging to that same wall there. Okay, so you can see here the weight of this person is coming downwards. It is represented as T, and then the tension in this cable towards the wall is taken as T1, and then tension in this cable towards the person is taken as T2 over there. And then the angle of T1 with respect to the wall is 15 degrees, and the angle made by T2 with respect to the horizontal is 10 degrees. Okay, so this is how the free body diagram of the given figure is represented. Let me write it once again. So this is my weight of the body, and then this is my T2, and then this is my T1 over there. Okay, so I'll just draw a perpendicular here. This is my 10 degrees over there. Okay, so and then I'll just draw a perpendicular or the vertical line here. So this is my 15 degrees over here. This is called as T1, and this is called as T2, and this is also called as W. Once you write all these values, then the free body diagram will be complete. Similarly, we have the example towards the right hand side. A pencil is resting on the floor over there or on the ground. Okay, the weight of the pencil is coming downwards, and then the reaction is moving upwards. The free body diagram is written towards the right side of the pencil over there. That means there are two forces which are acting there. That is self weight of the pencil, and then the next one is some more example for free body diagram for different cases here. Okay, we have two cases displayed on the screen. To the left column we have the actual figure, and towards the right side we have the free body diagram of the actual figures over there. Coming to the first example, there is a ball resting on the ground floor. Okay, so we have to draw the free body diagram for this example there. Okay, you can see there the weight, the ball has certain mass, or else the weight over there that will be acting downwards, and then you'll be getting a reaction force from the floor to the ball over there. So that is represented as here. Okay, the weight of the person is coming downward, sorry, weight of the ball is coming downward, and then the reaction from the surface to the wall is coming upwards. This is the free body diagram of this figure. So coming to this figure, you can see there is a ball hanging towards the wall over there. So it is tied with the help of rope over there. Okay, so let us draw the free body diagram for this one. So this is the ball here, the weight of the ball which is acting downwards, and then it is tied to a rope there. The tension in this rope is taken as T, and then it is always acting towards the support condition. This is my support condition. This rope is tied to this support here. That's why the force will be acting towards the support here. And then there is one more force, that is the reaction force coming from the wall towards the wall over there. That is represented as R there. So these are the three forces which are acting on the ball. So this is my free body diagram of the given figure over. Next example for free body diagram is, you can see here a ladder has been resting on the floor, so on the wall here. This is my wall, and then this is my floor here, and then smooth and smooth. Okay, so that means the friction is more over there. Okay, that's why it is moving in this direction, and then the friction is very smooth here. Okay, and then the weight of the person is acting downwards. Okay, something is placed here. Let us consider the person is standing on the ladder there. So the weight of that person is 600 newton there. Okay, and then there is one more force which is acting here, that is force P on the ladder. Let us draw the free body diagram for this one. Fine. So the ladder is in contact with the surface here and then is in contact with the wall here. Okay. So at two contact surfaces, we have reaction force. Let us see here. This point we have the applied force and then the reaction force, which is named after R2. And then coming to the top side of the ladder, there is a reaction force coming from the wall there. Okay, so the next one is weight of the person, which is coming downwards. Okay, so apart from the weight of the person, there is one more force, that is 600 Newton, which is shown in this free body diagram. Weight of the person is moving downwards, and then extra force is also moving downwards. So this is the example for the free body diagram of this given case. This theorem states that if three forces acting at a point are in equilibrium, then each force is directly proportional to the sine of angle between the other two forces. Let me repeat it once again. If a body is in equilibrium under the action of three forces, each force is proportional to the sine of angle between the other two forces over there. This theorem, that is Lami's theorem, is applicable only when there are three forces. If there are two forces, this theorem is not applicable. If there are four forces, then this theorem is not applicable. This theorem is applicable only if the number of forces are three over there. Okay, so let me write the formula for this theorem over there. Okay, so before going to the formula there, let us see the diagram for this Lami's theorem. Fine. So there's a point here. So this Lami's theorem is applicable for coplanar concurrent system there. Okay, coplanar means all the forces are acting at a single point. Sorry, are acting on the same plane, and then all the points are acting at a same point over there. Fine. So you can see here there are three forces which are acting at this point, that is P, Q, and then R. These are the three forces which are acting at a point center at this point. Okay, so let us see what is the angle made by P and Q. It is gamma, P and R it is beta, and then Q and R it is alpha. So alpha, beta, and gamma are the angle made by the two forces. So let us go back to the Lami's theorem. It is if a body is in equilibrium under the action of three forces, these are the three forces, then each force is proportional to the sine of angle made by the other two forces. Okay, so let us go to the statement here. So P by sine alpha. Alpha is the angle made by opposite forces, that is Q and R, sine alpha. Q divided by alpha, P angle made by the other two forces, that is P and R. It is beta. Next one is R. The gamma is made between P and Q. These are the opposite forces. So that means P by sine alpha is equals to Q by sine beta is equals to R by sine gamma. Okay, so this is Lami's theorem. You can see one more figure written over there. Okay, so we can see X, Y, Z are the angle made inside the triangle over there. So there are three sides, AB, BC, and CA. So in that case, what we have to do is P by sine X is equal to sine 180 minus alpha is equals to sine alpha. Okay, what we are doing is we are finding out the angle between two forces over there. Okay, so sine y is equals to sine 180 minus beta, it will be sine beta. Sine z is equals to sine 180 minus gamma is equal to sine gamma there. Okay, So finally, what is the equation here? P by sine alpha is equal to Q by sine beta is equal to R by sine gamma is equals to constant. So this is regarding the Lamis theorem. I'll repeat it once again. If a body is in equilibrium under the action of three forces, each force is proportional to the sine of angle made by the other two forces. This law or this theorem is applicable only if the number of forces are three. Let us see some of the examples on this Lamis theorem. Okay, the first example is a sphere of weight 100 Newton is tied to a smooth wall by a string as shown in figure. Find the tension in the string and reaction of the wall. As I said earlier, whenever we want to solve any problem here, first thing is we have to draw the free body diagram. Let me write the free body diagram of this given figure. Okay, so this is, I'll idealize this this given ball into small circle over there. Okay, solid circle. So the weight of this ball is acting downwards. So this is my weight, that is W. Weight is given as 100 Newton here. Okay, so next one is, you can see there is a reaction force coming on this wall, sorry, from wall to ball over there. So this is taken as R, and then there is a force which is acting on the string towards the wall is the tension in the string over there, that is represented as T. So this is my free body diagram. Free body diagram is not yet complete. Okay, so let me draw it once again here. That is, what changes I'll do is, this is my W. I'll take reaction towards this side. Both are same. Towards this direction also it's same. Here also it is same. I'll draw the tension like this. This is my T. Fine. So what is the angle made by the string with respect to the wall? It is 15 degrees. So what we have to do is, in order to use the Lamis theorem, we have to find out the angle made by the all the three forces, between two forces. Okay, so these two forces, the angle made by these two forces is 90 degree. Okay, suppose if this is 15 degrees, what will be this angle over here? Okay, so let me draw a small perpendicular here. Okay, so this will be what? 15 degree. This will be also equal to 15 degree. Now if this is 15 degree, what will be this angle? It is 90 plus 15, that is 75 degrees. If this angle is 15 degrees, this will be 15, and then this will be 75 degree. Okay, so the angle made by W and R is 90 degree. The angle made by T and R is 75 degree. Next, the angle made by T and W is, if this is 15 degrees, this will be 75 degrees. So the angle, total angle made by T and W is 75 plus 90 degree. So it will become 165 degrees. Now we got three forces, and then we have the angle between the two forces. Okay, we'll apply Lamis theorem now. Fine. So Lamis theorem. So Lamis theorem states that force is directly proportional to the sine of angle between the other two forces. Okay, so let us take the first force, that is T. T is equal T divided by sine of the other two forces. Which are the other two forces? R and W. It is 90 degree. So is equals to R divided by sine of the other two forces. That is 165 degrees. Next is T is over, R is over. Next one is W. W divided by sine of 70. Sorry, it is not 75 here. So it is 90 plus 15. It is 105 degrees. This is 105 degrees. Okay, sine of 105 degrees. So now we have to find out what T here. Okay, so we have to find out R, we have to find out T there. Now what is known in this given three set of equation? W is known. So what I'll do, I'll take T by sine 90 is equals to W divided by sine 105. So when I take this one, I'll substitute T is equals to W into sine 90 divided by sine 105. So sine 90 is 1 there. Okay, what is the value of W? W is 100 divided by sine 105 degree. You are going to get the answer as 103.53 Newton. That is the value of T there. Okay, so next what we have to do, we have to find out the answer for R. So for that what I'll do, I'll take it as sine T by sine 90 is equals to R divided by sine 165. So this is equal to R is equals to, you are going to get the answer as T by 90. The answer for T is 103.53 divided by 1 into sine 165 degree. You are going to get the answer for R as 26.80 Newton, which is same as that of displayed on the screen. The answers for the each problem will be displayed on the bottom right of your screen. This is how Lami's theorem is applied to the given problem, and then we found out the tension in the string and then reaction of the wall over there. So I told you the very first step is to write the free body diagram. Without writing, let us go to the second problem. Determine the horizontal force P to be applied to a block of weight 1500 to hold in its position on a smooth inclined plane AB, which makes an angle of 30 degrees with respect to the horizontal. So what is that we have to find out here? We have to find out the horizontal force P to be applied to a block of weight 1500 then. Fine. So now we'll draw the free body diagram for this case here. So let me draw the free body diagram here itself. So what I'll do is I'll just draw the axis here. This is my axis of reference. So here you are going to observe what? The reaction force from the inclined plane. So let me take this one as R, and then this is my force P there. Okay. So one more force, that is W, is acting here. That is weight of the block over there. So let me draw the free body diagram separately. Fine. This is my weight of the block, and then this is my force P, this is my force W, and then this is my reaction force R. These are the three forces which are acting here. Now we have to find out what is the angle made by each force over there. Fine. Now my inclined angle is 30 degrees, and then what is the angle made by P with respect to this one. Okay, so if this is 30, this will also be 30 there. So that means this angle is 30 degrees here. Fine. So I'll write it here. If this is 30, this angle is also 30 there. So I'll just drop a perpendicular from the surface of the block here. That is 30, and then this side will also be 30 there. Fine. So now the angle between P and horizontal is 30 degrees. The angle between R and P would be R to horizontal, it is 90 plus 30. So this will become 120 degrees over there. Fine. Now if this is 30, this will also be equal to 30 degrees. Fine. That is, this is also equal to 30 degrees. Now if this is 30, this will become 60 degrees. So the total angle made by P and W is 90 degrees here. Fine. If this is 30, this will become 60. The total angle made by R and W is 60 plus 90 is 150 degrees here. Now, with the help of these three forces, we can write the Laplace theorem there. Okay, so let me write one by one. R divided by sine of 90 degrees is equals to P divided by sine of 150 degrees, and then W divided by sine of 120 degrees here, and then weight is given here. We can find out the value P here. Okay, so let me write W equal to P by, sorry, P is equals to W by sine 120 into sine 150. So the answer for W is 1500 into sine 150 degree divided by sine 120 degree. You are going to get the answer for P as 866.03 Newton. So this is the answer for P. One more thing we have to find out here is, that is the reaction. So how to find out the reaction? With the help of the given set of equations here. So that is, I'll just write the equation for R. R is equals to W, that is 1500 divided by sine 120 degree into sine 90 degrees. Sine 90 degree is equals to 1, and then 1500 divided by sine 120 degree. You are going to get the answer for R as 1732.05, which is matching with the given answer on the slide. So this is how you have to find out the answer for problem number 3. A crate of mass 200 kg is to be supported by a rope and pulley arrangement as shown in figure 1. Determine the minimum required magnitude of force F and also find out the direction of F over there. Okay, so in this case, what they are asking? They are asking us to find out the value of F as well as the direction of F here. First, we'll draw the free body diagram for the given figure over there. Okay, so these are two pulleys over there. Okay, and then there is a crate of mass 200 kg, and then to these two pulleys there are two ropes tied here. This is one rope, and then there is one more rope there. Okay, two ropes are tied together for a pulley there. Okay, what we have to find out here, determine the minimum required magnitude of force. That is minimum required magnitude of force. Yep, this is the hint given in the question to solve the problem. Okay, we'll see it once we write the Leibniz theorem. And also we have to find out the direction of force with respect to the horizontal. As they have shown in the figure, theta there we have to find out the answer for theta and then value of f. So let us write the Lamis theorem diagram for this, free body diagram for this. Okay, so I'll take this one as my origin, and then this is my 200 kg weight. Okay, so first I'll convert kg into Newton. That is 200 into 9.81. I'm getting the answer as 1962 Newton force over there. Fine, this is my weight. That is 200 into 9.81. You are going to get the answer as 1962 Newton there. So this is my weight of the body. That is great. Next one is there is a force here. Okay, so let me draw the axis here. This is my axis, this is the angle theta here, and then I'll draw the dotted line. Dotted line is my axis over there. So this is represented as f, and here instead of two rope, what I'll do, I'll just draw a single line there. So the tension in each rope is taken as T, and then there are two rows. I'll take it as 2T there. Okay. If this angle is 30 degree, this angle will be equal to 30 degree. If this is 30, this will be 60 degrees there. And then this angle will be 90 degrees there. Okay, so this angle will be 90 minus theta there, and then this angle will be 90 degrees there. Okay, let me write the Lamis statement there. Okay, so I'll write it here. W divided by sine 30 plus theta. So this is my first force is equals to F divided by sine 90 plus 60, it is 150 degrees there, is equals to 2t divided by sine 180 minus theta there. Okay, so it is 90 plus 90 minus theta, so it is 180 minus theta there. So now here we have only one known term. Okay, that is W. The unknown terms are F, theta, and then 2 theta. So what we have to do is first I'll take this term, that is F equal to, so let me write it here, that is F is equals to 1962, that is weight, into sine 150 degrees divided by sine 30 plus theta then. Okay, so in the given question, what is asked here is find determine the minimum required force, that is magnitude of force. When the force will be minimum there, if sine of this will be maximum. When sine of this will be maximum is 90 degree. Okay, if this term is becoming 90 degree, sine 90 degree, this term will become minimum there, that is f term will become minimum. I'll take it as f equal to 1962 into sine 150 degree. I'll repeat the sentence once again. Determine the minimum required magnitude of force, that is we want minimum force here. If when will be the force minimum, this term is maximum. If this term is maximum, force will be minimum. If this term is maximum in the sense sine theta should be sine 90 there. Sine 90 is what? 1 there. So I'll take it as 1. So the answer for F is 981 Newton there. That is 1962 into sine 150. You are going to get the answer as 981 Newton there. So what condition I have taken here is sine 30 plus theta is equals to sine 90 degrees. Okay, so I'll equate these two things and then I'll find out the answer for theta here. 30 plus theta is equals to 90 degrees. So my theta value is 90 minus 30 is going, we are going to get the answer as 60 degrees. Okay, this is how we are going to find out the answer for F and theta. So we have to read the question very carefully there. So we have to find out minimum required magnitude of force. When force will be minimum, the denominator term, if this denominator term is maximum there. Okay. So theta value is 60 degrees, F value is 981 degree, which is matching with the answers given in the slide over there. Problem number 4. Determine the forces included in the members AC and BC of the structure as shown in figure over there. Fine. Let me draw the free body diagram for the same figure over there. This is 500 Newton force. So this is TCB. Okay, TCB, and then this is my TCA. So what is the angle made by TBC, TCB and TCA with respect to the horizontal? Fine. Now, if this is 150 degree, okay, so let me draw it here. I'll just draw a perpendicular here. Okay, if this is 30 degree, this will become 30 degrees. Okay, so if this is 30 degree, the angle made by TCB and then 500 is 90 plus 30, it is 120 degree. So I'll write it as 120 degrees over here. Fine. So I'll just draw a perpendicular like this. If this is my 90 degrees here. If this is 90 degree, if this is 50 degrees, this will be 40 degrees. Okay, so I'll draw a perpendicular here. This is my 40 degrees here. Okay, if this is 30 degrees, this will be my 60 degrees. So the total angle made by TCB and TCA is, this is my 60 degrees. TCB and TCA is 100 degrees over there. Fine. Now, if this is 40 degrees, this will be 50 degrees. So the total angle made by TCA and then 500 is 50 plus 90, it is 140 degrees. Now we can apply Lamis theorem here. That is, let me write the equation for this. TCB divided by sine 140 degrees is equals to TCA divided by sine 120 degrees is equals to 500 divided by sine 100 degrees. We know the value of the third force, that is 500. Let us find out one by one answers here. Okay, so this is my TCB. TCB is equals to 500 divided by sine 100 into sine 140 degrees there. Okay, by substituting these values in calculator, we are going to get the answer for TCB there. 500 into sine 100, sorry, 500 into sine 140 divided by sine 100. You are going to get the answer for TCB as 326.35 kilonewton, which is same as that of answer displayed on the screen here. Fine, let us find out the answer for TCA. The TCA is equals to 500 divided by sine 100 divided into sine 120 degrees. So sine 120 degrees. Let us substitute this in equation, that is in calculator. 500 into sine 120 degree divided by sine 100 degree. So that is, we got the answer for TCA as 439.69 kilonewton. This is also matching with the answer shown on the slide. This completes my problem number 4 by using Lamell's theorem.
Thank you.